Welcome, my friends! In this video, we will discuss how to construct a confidence interval for the difference in means of two independent populations. By independent, I mean that the sample observations from the first population have no impact on the observations from the second population. Let's say our variable x is the number of minutes an introductory statistics student studies for an exam. We may have one sample that reveals that Grand Rapids Community College students study an average of 100 minutes, and a second sample that reveals that Grand Valley State University students study an average of 90 minutes. We assume these samples are independent as they come from different schools and should not affect each other in any way. The quantity we are trying to estimate is the difference of two population means, mu1 minus mu2, and the point estimate is the difference of the two sample means, x bar 1 minus x bar 2, which is 100 minus 90 and equals 10. The interpretation of the point estimate is that we estimate that GRCC intro statistics students study 10 more minutes on average than GVSU students. An example confidence interval might be 5, 15, meaning that we estimate with C% confidence that GRCC intro statistics students study between 5 and 15 minutes more than GVSU students on average. On a number line, the confidence interval would look something like this. The point estimate of x bar 1 minus x bar 2 is in the middle and is 10. The lower bound is 5 and the upper bound is 15. The margin of error is 5, the distance from the point estimate to either of the bounds of the confidence interval. At this point, I haven't showed you how to calculate the confidence interval, but we will look at how to do that very shortly. For two sample confidence intervals, there are three possible end results. If both values are positive, such as an interval ranging from 5 to 15, that means we are C% confident that the first population mean is larger than the second population mean. If both values are negative, such as negative 15 to negative 5, that means we are C% confident that the first population mean is smaller than the second population mean. If one value is positive and the other is negative, such as negative 15 to 5, we cannot conclude whether or not the first population mean is larger or smaller than the second population mean. Stopping to think about these rules, they should make logical sense. Take the first example. If the difference in sample means produces a confidence interval with two positive numbers, such as between 5 and 15, every single value in that interval is positive, suggesting mu1 minus mu2 is greater than 0 in all cases. The only way for mu1 minus mu2 to be positive or greater than 0 is if mu1 is greater than mu2. Thus the conclusion holds. The same kind of logic can be applied to the two other rules. Only when the number 0 is contained in the interval, such as in case 3, can we not conclude whether or not the first mean is greater or less than the second mean. Thinking of our confidence intervals in this way is very similar to the results of a hypothesis test, which we will discuss in more detail in future videos. There are three different methods of computing the confidence interval for the difference in means of two independent populations. In any of the three cases, the confidence interval is equal to x bar 1 minus x bar 2, plus or minus the margin of error. The only thing that changes is the formula for the margin of error, which is slightly different in each case. In all cases, we must assume a sample size of at least 30 from each of the two samples, or we must know that each individual population has an approximately normal distribution. If the population standard deviation is known for both populations, the error equals z times the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. In the real world, this situation is very unlikely, as the population standard deviations are almost never known. If the population standard deviations are unknown, the error is the same, except for we use a t-score instead of a z-score and s instead of sigma. The t-score corresponds to the level of confidence and degrees of freedom. The degrees of freedom technically should be calculated using this big scary formula, but using the smaller of n1 minus 1 or n2 minus 1 is a conservative approximation. If the population standard deviations are unknown, but there is a good reason to think that the standard deviations are equal, the error is t times s times the square root of 1 over n1 plus 1 over n2. S is the pooled standard deviation and can be found by this ugly formula. The degrees of freedom are n1 plus n2 minus 2. Let's look at some examples. A sample of 36 introductory statistics students from Grand Rapids Community College and 49 introductory statistics students from Grand Valley State University revealed that the GRCC students study an average of 100 minutes for their exams, and that the GVSU students only study an average of 90 minutes for their exams. Suppose the population standard deviation is known to be 20 minutes for GRCC students and 15 minutes for GVSU students. Construct a 95% confidence interval for the difference in population means. If we let sample 1 represent GRCC and sample 2 represent GVSU, we have the sample size N1 of 36 and N2 equals 49. The first sample mean x bar 1 is 100, and x bar 2 is the second sample mean of 90. The population standard deviations are sigma 1 equals 20 and sigma 2 is equal to 15. Since we know the population standard deviations, we have scenario 1, and we can use the z-distribution to create our confidence interval, which corresponds to this formula. Notice also that the sample sizes are both at least 30, so the central limit theorem tells us we can assume an approximately normal distribution, which is required. The confidence level is 95%, so our picture looks like this, with 95% of the probability in the middle and 2.5% of the probability in each of the two tails. The point estimate of x bar 1 minus x bar 2 is in the middle, which is 100 minus 90, or 10. We also know that the z-score corresponding to a 95% confidence level is 1.96 from my handy table. If you want to know how to calculate this value with a z-table or a TI-84 calculator, check out my videos in the description. Plugging into the formula, we have 100 minus 90 plus or minus the square root of 20 squared over 36 plus 15 squared over 49. On the TI calculator, or any scientific calculator, type in 100 minus 90 minus 1.96, square root symbol, which is second, and then we press this key here, 20 squared divided by 36 plus 15 squared divided by 49. On some calculators, you may need to close parentheses after the square root. Press enter, and you should get 2.23. Now we have to do the exact same thing, but just change this subtraction sign to an addition sign instead. On this calculator, you can press second, enter to bring up your previous calculation. Then scroll to the left and change the second subtraction sign to an addition sign. When you press enter, you get 17.77 rounded to 2 decimal places. So 2.23 is the lower bound and 17.77 is the upper bound. We can include the lower and upper bounds on our graph. Our conclusion is that we are 95% confident that the interval between 2.23 and 17.77 contains the population mean difference between the number of minutes studied for an exam at GRCC and GVSU by introductory statistics students. Also, we are 95% confident that the population mean amount of study time for exams is higher among GRCC introductory statistics students than it is for GVSU students, since both numbers in the interval are positive. Let's change it up slightly. Instead of GVSU students, now we have Western Michigan University students. The sample size for WMU students is 64, and the sample mean is 98. And this time we have the sample standard deviation instead of the population standard deviation, given as 20 for GRCC students and 25 for WMU students. Since the population standard deviation is unknown, we must use this formula. The degrees of freedom technically should be found by using this complicated formula, but instead can be conservatively estimated by either n1 minus 1 or n2 minus 1, whichever is smaller. In our case, n1 minus 1 is 35 and n2 minus 1 is 63. The smaller value is 35, so the degrees of freedom for our example is 35. The graph looks like this, with x bar 1 minus x bar 2 equals 100 minus 98, or 2 in the middle. Using a TI-84 calculator, we can find the appropriate t-score by using the inverse t function. Select second, distribution, option 4 for inverse t. The area is 0.975 since we need the area to the left, which is 0.95 plus 0.025, which equals 0.975. The degrees of freedom are 35. Go down and paste. Match this output on an older calculator like a TI-83, 0.975, 35. Then press enter. The t-score is 2.03. Plugging into the formula, we have 100 minus 98 plus or minus 2.03 times the square root of 20 squared over 36 plus 25 squared over 64. This simplifies to about negative 7.28 and 11.28, which are the lower and upper bounds on our graph. We are 95% confident that the interval between negative 7.28 and 11.28 contains the population mean difference between the number of minutes studied for an exam at GRCC and WMU by introductory statistics students. Also, since one of the values in our interval is negative and the other is positive, we can't say whether or not the population mean study time at GRCC is higher or lower than the population mean study time at WMU. Okay, one final example. Assume the exact same information, except now, even though the sample standard deviations are slightly different from GRCC and WMU, we will assume that they are the same in the population. We now use this formula, which is appropriate when the population standard deviations are unknown, but we have reason to believe that they should be equal. The graph looks the same as it did in the last problem. The degrees of freedom are n1 plus n2 minus 2, which is 64 plus 36 minus 2, which is 98. The t-score can be found by going to second, distribution, option 4 for inverse t, 0.975, which is the area to the left of the upper bound, 98 for the degrees of freedom, and then we can go down and paste, and pressing enter gives us the t-score, which is about 1.98. The difficult part of this formula is finding S, the pooled estimate of the standard deviation. Since we are assuming the standard deviations are equal, we have to calculate some sort of average standard deviation between 20 and 25, which we can do with the help of this formula. Plugging in and using the calculator, we have the square root of open parentheses twice, once to represent the top of the fraction, and once to represent the parentheses in the formula, 36 minus 1, close parentheses, 20 squared, plus, parentheses, 64 minus 1, parentheses, 25 squared, close parentheses for the numerator, divided by, open parentheses, 36 plus 64 minus 2, close parentheses, and potentially close one more set of parentheses for the square root on some calculators. We see that we get 23.34 rounded to 2 decimal places, which is our pooled estimate for the standard deviation. Now plugging into the confidence interval, we have 100 minus 98 plus or minus 1.98 times 23.34 times the square root of 1 over 36 plus 1 over 64, which simplifies to negative 7.63 and 11.63. These are the lower and upper bounds on the graph. Our conclusion is that we are 95% confident that the interval between negative 7.63 and 11.63 contains the population mean difference between the number of minutes studied for an exam at GRCC and at WMU by introductory statistics students. Again, we can't say anything about whether or not GRCC or WMU students study more, as the interval contains both a negative and a positive value. Alright, my friends, we have finished our discussion of the confidence interval for the difference of means of two independent populations. We will be exploring many more fun and exciting statistical topics that you won't want to miss, so make sure to check out our other videos.